go. Hi, everybody. Let me turn this off real quick. So I'm looking over the chat, and so I can't give you just topics, because the point of the review isn't to just repeat the lecture. You can watch the lecture videos on your own if you need to review those things. If you have specific problems that you want me to go over, I'm happy to do that. So, like, draw the Lewis structure of this thing. Like, that we can do. But can we go over the ideal gas law? There's not enough time to do that. If you have a specific question, then I can definitely do that. I'm going to scroll back up here because somebody had a question about naming stuff here. So, oh, I got to move this out of the way too. Oh, I also need my tablet. But yeah, while the other questions are going, if you are like, oh, I already know how to do this, I don't need to review this, let me look up something. Go ahead and keep posting questions in the chat. I'm happy to go over things, but I do need specific problems because it takes me a long time to create problems. Like, sure, I could make up problems about molarity or whatever it was, but you'd have to come back in 30 minutes. Because I had to sit there. First, I had to write the problem. Then I had to do the problem myself to make sure it's doable. And then I have to make sure that there aren't like any weird exceptions or something like that, depending on the topic. Molarity, this wouldn't happen, but and then I can present it. So, like, writing an exam for you guys takes me like all day. All right, so this doesn't show up when I highlight it and click elsewhere, so let me fix that. So we're going to name compounds with Roman numerals. And, of course, my Photoshop is going to be all slow and sluggish. Let's see here. Oh, you know what it'd be better to do? Let's do it this way. So, when do you use Roman numerals? All right. So, which elements use Roman numerals and which ones don't? So, first of all, we use Roman numerals for metals, except for the following metals. Group 1 and 2, or aluminum. And that's it. Now, some textbooks include these as well. But for our purposes, ignore this. That's supposed to be a line through it. There we go. So, for example, if I said, name this, and we'll use aluminum bromide because that's on the screen here. We would say, okay, well, aluminum is always +3 because it's in group 13. And bromine is always -1 because it's in group 17. And we can remember that by saying, okay, if I draw the Lewis structure, and then I try and get an octet, removing electrons from something gets an octet. And then for bromine, here's what bromine looks like, 7 valence electrons. If I add an electron, I get its octet. So that's how I know what ions these form, because these are all known. And then I would just name this. Well, aluminum is one of our ones that we don't use a Roman numeral for, so I just write its name. All right, so there's that one. But let's suppose that you wanted to do something like this. You know that bromine is still -1. But iron could be anything, right? That one's not known. So what we had to do in this case is we had to deduce its charge by figuring out what all the other ions are. So here's all my bromines. And we know the total charge on an ionic compound is 0. So therefore, if all my minuses add up to that, -3, my iron must be +3. And so that would make this iron, parentheses 3, bromide. And so that's when you use Roman numerals. Whenever you have a metal that is not one of these up here. Any other metal needs Roman numerals. And now I gotta scroll down to make sure that I'm getting questions here. So here are questions. Okay, good. These are good. Yeah, so I can definitely do these. Where were we? Okay. So those would be examples of naming compounds. When do you use a Roman numeral if it's not one of these metals? And then if it isn't one of those, then we put Roman numerals after the element. Remember, no space between the name and the parentheses here. So I'm trying to make my spaces exaggerated. This kind of looks like a space, but there's no space here. All right, let's see here. This wasn't a Lewis structure, so we couldn't do that. Let's see here. Yeah, here we go. So for this problem, we'll draw the Lewis structure of silicon diselenide. Oh, just a second. Sorry about that. I had to step up for a second. Okay. We're going to count valence electrons here. So how many valence electrons does silicon give you? You'll need the periodic table to do that. Remember, it's the ones digit of whatever group it's in. Well, silicon's in group 14. So it would have 4 valence electrons. I'll just write group up here. Selenium is in group 16. And so each selenium would give you 6 valence electrons. And so we total those together. And we have 16 valence electrons. So when drawing the Lewis structure or something, the first step is always tell me the number of valence electrons, because that's how many you're going to get to. That's how many you're going to get to incorporate in your structure. Then we draw our framework, and our framework is going to have the first atom in the middle, and the other ones will go outside. Where on the outside, we don't really know until we build the structure. So just stick them anywhere for now. Okay. Next, we're going to bond them, and bonds are 2 electrons each. So I paid 4 electrons for each of these bonds. And then what I'm going to do is I'm going to put the remaining electrons on the outer atoms, and then anything that's left goes on the inner atoms. So I'm going to go 1, 2, 3, 4, 5, 6. That one could have been better. There we go. So I've used half my electrons, 7, 8, 9, 10, 11, 12. Now I've used all my electrons, so this is all I get. I was able to get octets for the outer atoms, but I have a problem. I don't have an octet for the inner atom. So what I need to do is I need to take some unpaired electrons and Or, sorry, not unpaired. I need to take some non-bonding electrons and put them in as double bonds so that silicon can get an octet. And so that's going to look like this. We're going to erase you. And we're going to put you here. And then we'll erase this one. And we'll put it here. And there you go. Everything has an octet, so there's the structure. All right. So let's see here. So this is all before I said be more specific. We just did this part, Elizabeth. So if you have more specific questions like how to name different compounds, we can do that. Let me know. And then I want this to be as close to the bottom as I can. Okay. Yeah, like that. That's perfect. We can go over that at the end. Let's see here. There we go. So we'll start at the top here. So for this problem, we have a balloon that is some volume at a certain temperature. What temperature would it need to be heated to in order for the balloon's volume to become that? So if I suspect that the most common problem for this type of problem is that for gas laws, you have to use Kelvin. Remember, Celsius is no good for chemical conversions. It's helpful for us to like conceptualize stuff, but as far as science is concerned, Celsius is worthless to us. Because if you divide by temperature and you divide by 0 Celsius, your formula breaks, right? You can't divide something by 0 and get a number out of it. So we have to use Kelvin. And the formula for Kelvin, which we went over way at the beginning of the quarter, is that the temperature of something in Kelvin is whatever its Celsius temperature is plus 273.15. So let's write down a little grid here. And we'll use our formula to solve for whatever is needed. So I have the initial volume is 2.86 liters. So we'll write that down. And it's at 23.3 degrees Celsius. But we can't use Celsius, so we need to use Kelvin. And I don't know where the calculator went. There it is. So I have a periodic table in the way. I'm trying to move it. There we go. 23.3. That's not 3. Plus 273.15. Now remember sig figs, so my first number only went to the 10th place, so I'm only going to keep that to the 10th place. So this would be 296.45, which we would round up to that. So there's our temperature in Kelvin. And then the question's asking us... Oh, I just realized you can't see the problem that's on the top here because it's scrolled off the top of the screen here. So this is the problem that I'm doing right now. So the final volume is 6.82 liters. And then we need to solve for this. All right, how do I solve for T2? I need to first get it up here, right? And then I need to get rid of this stuff. So if I multiply both sides by T2, I would get this. T2 times V1 over T1 equals V2. And then I'll just divide both sides by V1, so this will go down here, and this will go up here. And my formula would look something like that, right? And now all I have to do is just plug in the numbers. Oh, I ran out of space already. Look at that. So V2 was 6.82. V1 was 2.86. These are both in liters, which will cancel. Times 296.5 Kelvin. And what do we get for that? So I get 707 Kelvin. Which I can then turn back into Celsius by subtracting 273. I get 434 Celsius. So I would have to heat the balloon to 434 degrees Celsius in order to double its volume. Or not double its volume, sorry. To increase its volume by that, to that much, from 2.86 to 6.82. This is, of course, assuming the balloon doesn't break. All right, any questions, let me know. All right, so we got this motorcycle problem. I got to scroll all the way back up to the top here. All right, so it takes a motorcycle 32.9 minutes to travel from Everett to Seattle. And the speed is 63.1 miles per hour. And I want to know the distance in centimeters. All right, so I have here, this is a time, and this is a distance. And then this unit right here converts distance to time. Oh my goodness, why isn't this working? There we go. So what should we do to solve the problem? Well, if I was given one of these two things, either distance or time, I could solve for the other one using this conversion, right? Well, I'm given the time, so we're going to start with that. And I am given a number of minutes, which I could turn into this unit of time. And once I have hours, I can then turn that into miles. And now I would know how far the car went, or the motorcycle, or whatever. But I don't want miles, I want centimeters, so I will just convert that to centimeters. And that should give us the answer to the problem. So let's do that. So let's set up the units each step. So we'll turn minutes into hours. How many minutes are in an hour, though? 60 minutes per hour. Okay, that's good. All right, then we'll turn hours into miles. How many miles are in an hour? Well, normally that wouldn't make sense, but since we have a specific speed here that we're going 63.1 miles per 1 hour. And we're all set there. Okay. Now I can turn miles to kilometers. This one we'll have to look up on Google. I think it's 1.609, but I never remember. So miles to kilometers. 1.609. There we go. And then finally we can do... Oh, well, not finally. We have to go to meters now. And then centimeters. Now, you can do all the units at once if you wanted to. So in a kilometer, there are 1,000 meters. And in a centimeter, there are 10 to the minus 2 meters. And of course, my pen decides, nope, it doesn't want to function. There we go. All right, we'll type all this into the calculator. 32.9 times 63.1 times 1.609 times 10 to the 3 divided by, parentheses, 60 times 1 times 10 to the minus 2. And so we go that many centimeters. That's not really super helpful. So I'm going to write it in scientific notation. I get 3 sig figs here. So this is 3 sig figs. This is exact. I get 3 sig figs here. 4. And then these are exact. So this is the smallest. So my answer should have 3 sig figs. So that would be 5.57 times 10 to the 6. There you go. Now, our answer makes sense here because it should be a really large number of centimeters. A centimeter is tiny, yeah? Like, if you have a yardstick or a meter stick, a yardstick has like 90-something centimeters on it, and a meter stick obviously has 100 centimeters. You could do a lot of meter sticks from Everett to Seattle, right? If you just went down the highway going 1, 2, 3, flipping it over each time. Yeah, you do that thousands of times, right? So it makes sense that you'd have millions of centimeters. All right, so now we're here. How many grams of... Oops, I scrolled it off the screen, sorry. How many grams in a sample of chromium metal containing 3.18 times 10... I'm assuming this is 10 to the 24 atoms. Otherwise, that doesn't work. But... All right, so we have 3.18 times 10 to the 24 chromium atoms, and we want to know how many grams are in the sample. So we know that if I know the number of atoms of chromium, I can turn that into moles of chromium, which I can then turn into grams of chromium. So I can do a unit conversion like this, and in 1 mole of chromium, how many of anything are there? There must be Avogadro's number of atoms per mole. That's true no matter what it is. And then next, we can turn moles of chromium into grams of chromium. And I still have my periodic table here. How many grams of chromium are in a mole? It says 51.996. And so we can type that in. Divided by Avogadro's number. And we get, we don't need exponent mode anymore, 274.57. And I should have 3 sig figs based on this first number. So 275 grams of chromium. All right, so next, if we have this many moles of C5H12 are reacted with abundant O2, how many moles of CO2 are produced? So we got to write a balanced equation for that. So we got C5H12 plus O2 makes, and we know that the products of a combustion are CO2 and H2O. That was mentioned in Chapter 9, probably in the slides that I had linked to a video. And so we need to balance this. All right, so I've got 5 carbon, 12 hydrogen, and 2 oxygen. And over here I have 1, 2, 3. So first move, well, balancing carbon should be pretty straightforward, right? We'll just do that. So this becomes 5. And then 5 times 2 is 10, plus 1 is 11. So I get 10 plus 1, which becomes 11. Then the next step would be to balance H. I have 12 over here and then come in pairs, so this makes 12. So that's balanced. But now I have 5 plus 2 is 10, plus 6 times 1 is 6. So I have 16 oxygen. We'll just erase all that and put that down. And then finally, I can balance oxygen, which I do by just doing that. So if this is all balanced and correct, then our problem would be asking us if I have 5.49 moles of this, and I wanted to figure out how many moles of oxygen reacted with it, I would do something like this. These units would cancel out. And I turn them into moles of O2. Oh, I'm sorry. We wanted to do how many moles of CO2 are produced. Well, I do this then. Because for every 1 mole of C5H12 I burn, we're going to produce 5 moles of CO2. I thought we were trying to figure out how many moles of O2 we needed. I didn't read the problem. So there you go. So we're going to multiply that number times 5. And we get 27.5 moles of CO2. All right, next we have, let's see here. So we just did this. So let's see here. The cost of a pure metal is this much. What volume of metal costs that much? Here's the density. Okay. So this is the metal I'm buying. I have this much money available. And I'm trying to figure out what volume I can buy of that metal. And I know that the density is equal to 14.2 grams per cubic centimeter. All right, how do I solve this? Well, let's look at what our conversions do. So this conversion converts mass to volume. And this conversion converts money to mass. And I want volume, and I've got money. So could you see that I could do something like money to mass to volume? From that, because I would turn this one into this, and then turn the mass into a volume. So let's do that. So I'm going to turn money into mass. So $5.01 per kilogram. And then I can turn mass into volume, but I have to have mass in grams because that's what it is right here. So we'll do that first. There we go. And then we'll turn grams into cubic centimeters using the density right here. And so that is 14.2 grams per 1 cubic centimeter. That will give us a volume in cubic centimeters, and we'll just type it in the calculator. 1 over that, 14.2. So we get 2,192.79 cubic centimeters. I only get 3 sig figs because of 2 different numbers, so I'll write that. There you go. All right, the next one. Oh, we're out of space again. Hold on. Back to the top. Why didn't that erase? There we go. I don't know why that took 3 tries. All right. 45.4 grams of KOH are added to enough water to produce 394.5 milliliters. What is the molarity of the solution? So molarity... Oh my goodness. Sorry. I hate this pen right now. There's the formula for molarity. We need to know the number of moles of solute, and we need to know the liters of solution. So I need to turn this into moles of KOH, and I need to turn this into liters of solution. So we can do those 2 steps. So for the moles, we would say, okay, well, I have this many grams. And we can look up on Lentech how many grams there are per mole of KOH. So I'm going to type that in. We should all know where Lentech is by now, and if not, you can Google it. But when I type in KOH, I get 1 mole is 56.11 grams. So that would tell me my number of moles. And that is 0.809. All right, we got that. And then we have 394.5 milliliters, which we need to turn into liters. And we know that in a milliliter, there are 10 to the minus 3 liters. Which tells us that much is our volume. And then finally, I just take those two numbers and I put them together. So the moles solute is 0.809. And then our volume is 0.3945. So we'll take 0.809 divided by 0.3945. And I get 2.05 moles per liter. All right. And then this last one right here, naming aluminum carbonate. You've already given it the name, so I'm not really sure. Did you read the formula? So aluminum has this charge, and carbonate has this charge. So if I was going to put them together, I would need this many of each so that the charges balance. And this would be aluminum carbonate, or Al2 carbonate with 3. Sorry, I wasn't sure what you meant by the last problem. So hopefully that's what you meant. All right, so those are a sample of problems that could come up on the exam tomorrow. What we're going to do is we're going to take a break. I'm going to put this back on the screen. I'm just going to let it sit here for at least 10 minutes. And if we have more questions when 10 minutes are up, I won't put the timer on the screen here, but I will start the music up again. So type any questions you might have during the break, and I'll check back in. And if we're all done with questions, then we're all done. Great. So I'll see you in just a little bit. clicked on the wrong one. There we go. All right. So I got one question during the break. So that was this aspirin question. And we'll go over that. So let's see here. So I have acetyl salicylic acid, which is C9H8O4. And I have 313.8 milligrams of this, which is the same as this. We'll just skip that. And then I want to find out what mass of that is carbon. So I know that in this many grams of C9H8O4, I can turn that into moles. So if I have grams of acetylsalicylic acid here, or actually this is acetyl salicylate, I think. No, it's acetylsalicylic acid. Okay. So we're going to turn this in grams into moles. And then I know that from moles of however much of this I have, I could get moles of individual parts. So I could say, for example, 9 moles of carbon per C9H8O4, or 8 moles of hydrogen, or 4 moles of oxygen. And we can tell that because of these coefficients, right? Well, we want carbon for this problem. So we could figure out the mass. So let's do that. So how many grams are in 1 mole of C9H8O4? We'll go to Lentech to do that. I got 180.16. And then I also know that there are some number of moles of carbon per C9H8O4. And it's just this number right there. In 1 mole of the big thing, how many moles of carbon? 9, because I wrote it in my formula. And then finally, we can say in a mole of carbon, well, after I cancel out my units here, there are 12.011 grams of carbon. And doing this calculation will give me the mass of carbon. And that is 3138 times 9 times 12.011 over 180.16. So I get that, which then becomes that, depending on what the answer, what the units of the answer you want are. There it is, okay. All right, and then Lewis structure for SiO2. So same as SiSe2 because it has the same number of electrons. So you can go back and see what that one was. If you are curious. There we go. And then can we do polarity and molecular plus Vesper geometry? Sure. Okay. So first let's do polarity. So which is more polar, silicon, or which is more electronegative, silicon or oxygen? And of those two, oxygen is more electronegative, so we would have polarity look like that, and like that, And so if I were to combine these polarities, one is pointed in this direction and then the other one's pointed right back in the other direction. I ended where I started, so this is nonpolar. And then for Vesper Geometry, wow, none of those pen strokes came out. There we go. For Vesper Geometry, there are 2 electron groups, which makes it linear. And of those 2 that I circled, none are electron pairs, which means that its molecular geometry is also linear. So this is a linear molecule. All right, it looks like I don't have any more questions, so this is going to be last call for questions. I'm going to mute myself, put the music back on. I said I was going to put the music on, and I did, but I also had the video muted so nobody could hear anything. Yeah, it looks like we don't have any more questions, so I'm going to go back over here. I did want to thank everybody for coming to the review session. This will still be on YouTube, so you can watch it later. But that's pretty much it for Chem 121. So this is the last video. This is the last time you'll hear my little outro music. The final exam is scheduled for Thursday. Make sure that you let me know as soon as possible if you need another day. So available days are Wednesday, Friday, Saturday. Yeah. Lab number 5 is due Wednesday, and it closes Thursday. That is your day of your final, so don't let all that pile up at once. And final grades will be posted by Tuesday next week. So that's all I got. Hooray! It's almost over. Hang in there, and we'll see you on the other side. Take care, and thanks for the quarter.